Hello everyone, I hope I'm audible to you. So we'll start today's session, and if anybody else is joining, they can join eventually. And I'm really sorry for the abrupt stop of last session. There was some problem with the Google Meet duration. So if today's session is being restricted to 1 hour, then what I'll do is before the 1 hour gets over, I will put on a link, a new Google Meet link in the chat box, so that when this link expires, immediately you can join in using the other link. Okay. Last time I tried to do it with the same link and that didn't happen, so I'm really sorry for that. So yeah, so I'll share the screen. Just let me know if you can see it. Is the screen visible?
Yes, ma'am.
Okay,
Yes,
thank you.
ma'am.
Okay, we'll start. Just give me 2 minutes. I'll join in from my phone so that I can admit whoever are coming. All right, so I'll start. If there are any interruptions or if you have any queries, you can put it in the chat box, or even in between, you can just ask me. So we'll begin. So, welcome to the week 3 problem solving session for Geographic Information Systems. The instructor is Professor A.K. Saraf from IIT Roorkee, and I'm the teaching assistant Anshana from IIT Kanpur. So today we'll be looking or discussing the topics from week 3, and we'll discuss very few problems, because the theory is a little elaborate this time. So hopefully when we discuss, it will help you with the problem solving of the quiz or the assignment. So yeah, so in week 3 we are starting with the raster data compression techniques, and then we'll be discussing about georeferencing and how the data is managed or processed. Such topics we'll be covering in today's session. So you might be familiar with the uh, term compression. Like most of us, we use like when we are downloading a very huge file from the internet, we see that it doesn't download as such. In fact, it downloads in a compressed format. So compression is mainly done to save time and space, because there might be huge files which if you are trying to work with, it's going to be difficult. So in order to make it easy for you, this data compression is done. That can be done for text files, and at the same time it can be done for image files. So today we'll be predominantly discussing about raster data compression techniques. So that is what I have given here. So why do we need compression? Because large amounts of data can create enormous problems in storage space and transmission time. So if you can see, like I don't know if you have ever worked with a very huge file, but whenever we open such files, it takes a lot of time to open it, and whenever you are doing some function or the other on that particular file, that also takes a lot of time. So if you are not looking for such a huge space occupying file and you just need a part of it, then compression comes handy. Okay. So all raster or image compression or encoding techniques attempt to get rid of the inherent redundancy, which may be spatial, spectral, or temporal in nature. So unlike vector data doesn't provide that much compression. Like vector data compression is also done, but compared to raster data compression, vector data compression is not as much because the repetitiveness is not that predominant in case of vector data. Like in raster data, for example, let me just show you. So if you remember from the previous session and also from the lectures that are posted, so uh, we represent the raster grid like this. This is a very idealistic one because not all images might have such well-defined boundary. Uh, it can be slightly of a different shape. Anyway, we have the square shaped unit cells in it. So what happens in case of this vector, raster data is that there is a possibility that this cell and then this cell, they might have a similar value, or this might also have a similar value, this might have a similar value. So the repetitiveness chance is more in case of raster data when compared to vector data. Vector data also can be compressed, but because of lack of redundancy or repetitiveness, it's not uh, that prevalent compared to raster data. Okay, so essentially we are trying to accommodate as much data as possible within whatever space is available or in a minimum space. For example, let's say you have a very small box like this, okay, a very small box. But then you have a lot of items that you have to somehow fit in this box. Or you can even imagine, like the professor had shown an example in which a person is trying to put a lot of things in the car boot space. Okay, so if that area is small and you have to put a lot of things in it, then what will happen? As much as you stuff things inside, they will get compressed, right? That is the same thing that we are trying to do in case of data compression. We are trying to fit in as much as data possible within whatever space or as minimum as space is available. Okay, so keeping uh, a lot of things in such small spaces will result in compression. Now, why like vector data is a little more discrete in nature? That is the reason why vector data repetitiveness is not that much present. But then raster is a continuous like data form. So in that case, there is a high chance of redundancy. So data is, this is just a recap of what we discussed about raster data. So data is classified as continuous, such as in an image, or thematic, where each cell denotes a feature type. And if you remember, I had given you an example, like for instance, if you have again, okay, sorry. If you have the, I don't know what is happening. Okay, so if you have a grid like this, and let's say this is a very theoretical explanation, not a real life one. So let's say the parts that I'm marking, let's say this is a forest cover. Okay, this is a forest cover. Then let's say this is a building area. Then we might have something else, some feature over here. So this is how like we are saying that the data can be either continuous like in an image, or it can be thematic like in land use like land cover data set and all. We might have such thematic representation. So there are numerous data formats like the TIFF, the GIF, or AirDAS.image, etc. So you're familiar with these, especially this form, you might be really familiar because we often use that while sending messages to our friends or colleagues. So GIF images are used. So there are different data formats. Raster data represent features as a matrix of cells within rows and columns in a continuous space. The same thing that I was trying to convey. So we have rows over here, then we have columns as you go. And one thing you have to keep in mind is that all this raster data images need not have this whole square feature. It can even be rectangular in nature, but then at the same time what you have to keep in mind is the unit cells will always be a square shaped one. That will not be compromised, but then the wholesome structure can be either square or it can be rectangle or something else. So raster data tends to be spatially autocorrelated, which means that objects which are close to each other tend to have similar pixel or cell values. The same thing that I was trying to convey. Like you have the grid, so the nearby grids have a tendency to have a same value. It can be or cannot be, but then there is a tendency that they might have the same pixel or cell values. So all things are related, but nearby things are more related than distant things. This was a statement given by Tobler in 1970, and because of this principle, we expect neighboring pixels to have similar values. Therefore, instead of repeating pixel values, we can code the raster as pairs of numbers. You will understand what I'm trying to say here when we are going to discuss the different techniques of compression. But essentially what we are trying to do is, for example, let's say you have a basket, okay? You have a basket in which you have like oranges. Okay. So you have a fruit basket, you have oranges here and there, then you have banana over here, then you might have some grapes, something like that. So it's like a mix of fruits over here. Now you are segregating it in such a way that you are keeping the oranges together in one place, you are keeping the bananas together in the another place, then you are keeping the grapes in another place. So this is basically what we are trying to do here. Like we are basically trying to combine the common or similar ones so that you don't have to account for each of the points, rather than you can just group them and then take it like that. So that is more easier when compared to accounting for each of the fruit for in this example. So this is a very simple example of a raster. So we have a lot of grids over here. Then we have this is a binary image basically. That is, you have a white portion and a dark area. Nothing more than that. Okay. There can be other complicated images, but we are giving the example using a binary image. So we'll be basically discussing 4 different techniques which is used in GIS software. There are many techniques, but then for the purpose of discussion, we'll be doing 4 different techniques, and we are taking this binary image as an example. Okay. So for this dark area, we'll be considering the value as 1, and for the white area we'll be giving the value as 0. Now you have to keep in mind the 0 and 1, like it doesn't have this numeric meaning, rather you're just giving a number, that's it. Like it's not some value is not there, it's basically an identity that you're giving. Okay, 0 and 1, that's it. So first technique that we are going to learn is the chain codes technique. Okay, that is one technique of raster data compression. Okay, so the boundary of the region can be given in terms of its origin and a sequence of unit vectors in the cardinal directions. Okay, so this what they're trying to say is, like, the cardinal direction is basically the north, south, east, west direction. Okay, so we'll be just giving it like this. So this is north, this is east, south and west. So what we are doing is the boundary of the region, like we'll fix the boundary of the region in terms of the origin and a sequence of unit vectors in the cardinal directions, that is in the direction like north, east, south and west. These directions are just given these numbers. Again, I'm saying these are just numbers. Okay, like we are not having any numerical value to it. This is just to identify the direction, that's it. So east is given the number 0, then north is given the number 1, west is 2, and south is 3. So just that number we are assigning to identify that, okay, if you say 0, that means the direction is east. Or if you say 1, the direction is north. If you say south, the direction is 3. I mean, if you say 3, the direction is south. If you say 2, the direction is west. Okay. So in chain code technique, what we are doing is, like, for instance, just again I'll draw it here so that it's easier for you to visualize. So we have north, east, west and south. Okay. So here it is 1, 0, 3 and okay. This is to remember, for you guys to remember. That's it. So now what we are doing is, the example given here is, if we start at row 10, okay, so this is row 10, okay, so and row 10 and column 1, so we are starting from here basically, and the boundary of the region is coded clockwise. So first we are fixing the boundary, right? So we are doing it in the clockwise direction. Clockwise is what? In this direction, okay, this is the clockwise direction. So we are going to fix the boundary in the clockwise direction. So first we are starting from this cell. So this cell will be considered as 0, like we are moving in the east direction. So this direction we'll move, then this direction we'll move, then this direction we'll move, like this, like this. So it's going to go on, so on and so forth. So first you are moving in this direction, so it is 0. Okay, then you are going up, which is north, so it will be 1. That is what is being given here. Okay, then we are going 2 steps in the, or 2 cells in the east direction, so it is represented as in this form. This is not, 0 square doesn't have any meaning, right? So that's why I was again insisting that this does not have a numeric value. This is just a representation. So this is 0 square. Then you are coming down, which is south, so that becomes 3. Then again we are going to in the east direction, so that's going to be 0 square, so on and so forth. I hope you understood how we are giving this notation. If you need any clarification, you can just stop me and ask, or you can even put it in the chat, how the chain codes technique is working. Okay, I think you are able to understand, or else, like, let's see. If you want me to repeat it, you can ask me, because we'll be discussing the techniques in detail. I'm hoping that you understood what I just said. Okay.
Excuse me, ma'am.
Yeah.
In that, ma'am, after coming 1 down, then why we are writing 2 successive zeros? We can write in the same way what we have write for the third sequence, no? 0, 2.
Which one are you asking?
Ma'am, in the when we are doing the coding, the second row, if you come to the second row, ma'am, like
You're
0,
asking
2.
this one.
Yeah, ma'am, in the second
Let me
row, no,
just see.
that coding.
Okay, so we reached this position, no? Then we went 1 up.
Up, yeah.
And then we are going 1 to the east. So that again becomes 0.
Yeah.
Okay, actually I think that might be a mistake, because then we have to come down actually.
Down, no?
Yeah.
Then down means again, yeah.
That should be 3.
3.
Then again 0. Yeah, so it might probably a mistake. I'll just clarify it, and then maybe I'll, if it is an error or if there is another explanation, I'll verify it and let you know.
Okay, ma'am. Thank you.
Okay. Okay, so Tobaya has asked me to repeat it. So I'll just once again tell you the gist of what I was trying to explain. So this is chain codes technique. This is a technique which is used for data compression, okay, raster data compression. So here we are using a binary image representation. Binary image is basically, here you have a white area. Binary is basically black and white. You see the black and white image, no? So you have black or white, that is the thing. So here we have a dark area and we have a white area. So this is the image that you have. So in chain codes technique, what we are doing is basically we are defining the boundary of that image. Here we are focusing on the dark area. Okay, that's why we are taking it like this. So we'll fix the boundary first. And how are we fixing the boundary? We are doing it based on the cardinal directions. Cardinal direction is north, east, south and west, which I have drawn on the PPT, like the slide. Okay. So for each of these directions, we are assigning some values, some numbers. It's not basically, we are not taking it as a mathematical value. We are just giving it that number for representation. So east is given 0, south is given 3, west is given 2 and north is given 1. Now what we are doing is that we are trying to assign the boundary of this dark area. So here the example is we are starting from row 10 and column 1. Okay, this is row 10 and this is column 1. Okay, so here we'll start from the first cell to mark the boundary. So here this first one we are going in the east direction, so therefore it will be 0. That is why I wrote 0 here. Then we are marking the boundary going up, so it is 1. Then we are going 2 steps to the right, that is in east direction, 2 cells we are covering, so it is 0 square. Then we are coming down, so it is 3. Then 2 steps we are going here, so that is 0 square. Then 1 step up, 1. And then now the doubt that was raised, so that I have to clarify. But if this is the technique that we are following, then this will be 0, then this will be 3, 0, 1 and so on and so forth. So basically our intention is to mark the dark area boundary. So finally we should be able to get this entire region. Okay, we will be marking the boundary like this. You can actually verify it. I'll clarify this one and I'll let you know in the next session. I also noticed it right now, so I'll do that. But otherwise you can also give it a try. I hope that is clear. If not, you can just again, okay, fine. Then the next technique is the run length coding or encoding or RLE technique. Okay, run length coding or encoding, either way it can be used, or in short form we say it as RLE. This is a lossless technique. What do you mean by lossless technique? That is basically if you have a very large file and you are compressing it using this method, it will get compressed, but at the same time none of the data is getting lost. Like when you compress it, most of the time what happens is there is a possibility that when you compress, some of the data might get lost. That possibility is there. But in the run length coding or encoding technique, this possibility is almost negligible. So this is a widely used compression technique for raster data. Okay. So the primary data elements are pairs of values or tuples consisting of a pixel value and a repetition count, which specifies the number of pixels in the run. I'll show you the example because these terminology might be a little confusing. I'm just discussing it here so that some things will stay in your mind. Data are built by reading successively row by row through the raster, creating a new tuple every time the pixel value changes or the end of the row is reached. RLE would be of little use for DEM data or images where neighboring cells or pixels almost have different values. So this is a lot of words given over here, but we'll see the practical example, so then it will be a little more easier. Only thing you have to remember is in this RLE method, we are going to assess the image row by row, and in that we will see how many repetitive cells are there, and accordingly we will name them, and then that names will be used for the coding. So again we are using that binary image that we had discussed. Okay. So in this case, what we are doing is the run length codes allow the points in each mapping unit to be stored per row in terms from left to right of a begin cell and an end cell. So in run length coding, you have to remember we are always going to move from left to right. Okay, and that too row wise, not column wise. We will be moving from left to right in each row. Okay, so here if you take the example of row 9, where is row 9? Yeah, So we are discussing the example of row 9. Okay. So in row 9, what we are doing is this is basically row 9, and first cell is white. So we are not considering that because we are looking at the dark area, right? So here we are just going to see where the dark area is present in row 9. Okay. So the representation, I think it should have been a comma. I might have mistakenly put it as hyphen because anyway. So here what you have to remember is in 2 and from 2 to 3 you have a dark area. So that is represented like this. Then the next dark area is coming in the 6th position. Okay. And that is only like this is kind of how do you say, how you write the coordinate system and all. So it's a similar thing but not exactly. So 2 to 3 we have, then 6 is basically only one cell is there, right? So that's why we have written it as 6. Okay. Then again it is coming from 8 to 10. Now if you take row 10, then you can see 1 to 10 it is completely dark area. So we have written it like this. Row 11, that is 1 to 9. So it is written like this. Again 12 is also 1 to 9. 13 if you see, it starts from 3 to 9. So 3 to 9 we have written. And 14, but I think we have to account for this also. They have not written it here. Anyway, this is 3 to 9 and then 12 to 16 is also there. Okay. Then in 14 we have 6 to 5 to 16, and in 15 we have from 7 to 14, and in okay, just hide this. Okay. And in 16 it is from 9 to 11. So that is how you have to sort of account for the dark area when you're doing the run length coding. So we are just assigning the positions. So here the same thing you can see. In this case it's a very simple binary image. So if you look at 1, 2, 3, 3, the same thing. Okay, 2, 3, 6, 6, 8, 10, then row 4 is 1 to 10, all those things. So this describes the interior of an area by run lengths instead of the boundary. So earlier in case of chain codes we were defining the boundary. Here we are just looking at the run lengths. Run length is basically what? That same color where at to what extent can you see in a single row. Okay, but this is easier because this is a binary image. But if you take a look at this image, that is a little more complicated. Here only you have this white color and this orange color or yellow color you can say. But here you can see yellow, green, blue, red, orange, all those colors are there. So how will you write the codes for this? So this is like a multiple attribute case, more options are available. Okay. So in this case what we are doing is, if you take a look at row 1, you can see each of the colors are given the alphabets, or they are assigned as X for yellow. This red color thing is given as Y, blue color thing is given as R, and green color thing is given as W. Okay. So in row 1 if you take a look at that, and row 1 is basically this row. Okay. So if you take a look at this, how many cells do the yellow color have, like initially? Like we are going to go in this row, right?
4. 4 cells.
Yeah.
4.
So that is the reason why we are writing it as 4x. Okay. X is the color, and first we have 4 yellow cells. Then like you said, the next two are green in color. So we have 2 and the code for green is W. So 2W. Then we have 3 blue. So it is 3 and R. And then we again have 1 yellow. So it is 1 and X. Similar thing, if you take a look at the second row, you can see there are 3 yellow initially. So it is 3X. Then we have 1, 2, 3, 4, 4 green. So 4W. Then 2R and 1Y. Okay. Then if you take a look at row 3, it is 2x over here. Then 1, 2, 3, 4, 5, 6, 6w, and then 2y. Then row 4, again 1, 2, 3, 4, 5, 5w, and again 5y. So that is how in this when you have multiple attributes, this is one way you can code it. Okay. There is another way also, like recording end cell position within a row. So that what we are doing is, for example, in this case, okay, first row if you take, X is there, and okay, so in case of X, where the X is ending in the first row, like uh, for example here 1 2 3 4 fourth position, uh, like the last cell position is 4, so x4 is written. For W the cell position is 1 2 3 4 5 6, so sixth position, and for R or blue it is ninth position, and again X is there in the 10th position. So here actually we are doing it in terms of numbers or number of color that unit cells, but here we are naming it in terms of the end cell position. So that's why I was saying these numbers that we are assigning over here doesn't have a numeric value. Like it's depending on how you're considering it. So because in the first case we were doing it based on the number of cells, but while in the second case we were doing it based on the end cell position. Is that clear? Okay. If any query is there, you can put it in the chat also. I think it is clear. So this is yet another example. So here we have a full raster coding of 256 values over here. So we have A, B, C, D, like 4 different categories we can say. All that is done. So first A, we will see in the first length it is completely all 16 cells are that one. So that is considered as the 0th row. Okay, 0. That is why 0 to 15 it is coming, because 15 0 to 15 means the count is 16 rows, but then yeah, we'll denote it as the 0 1 2 3 like that. So if you take a look at A, or in the 0th row, you can see that there are 16 cells all which have a color of A. Then again second row is also same. Third row, when you come, you can see it's not just A, you also have D present in it. So 14 cells have the red color, but then 2 cells have the green color. So we are writing it in this format, A and D, 14 2, then that row is 2 2. Although like in number, like when you count it is the third row, the numbering it is coming as 2. Okay. So like that we will give for all of these. And in that sense we can actually code it to like the full raster coding is 256 values, but when you do the run length coding it will come up to 129 values only. So that's like a very drastic difference, right? So compression can be done in that way. So that was regarding run length coding. Now we will do the block codes. So in block codes, the idea of run length codes can be extended to 2 dimensions by using square blocks to tile the area to be mapped. So if you remember in run length codes, what were we doing? We were considering each of the rows, that's it. So that's kind of like a one-dimensional approach. But in block codes, as the name suggests, we are doing it in a two-dimensional approach. That is, instead of just going or considering a row like this, we are actually considering a block. Okay, I will explain how it is done, but this is basically the essence. So first we'll start with the bigger blocks, and then we'll come down, and then we'll reach the smallest block, which is the unit cell block. Okay. Okay, so the data structure consists of just 3 numbers, position, just 3 numbers, position, the size and the contents of the pixels are stored. So here, if you take a look at this image, like this dark area that you can see, first you will try to draw the biggest block wherever possible. So here that biggest block that is possible is this one, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think it should have been 16. I don't know why they've written it as 17. It should have been 16. So this is the biggest block that is present. Okay. So 16 unit squares are there. Then the red blocks, which contains which contains 4 squares, that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 4 squares are there. One 16 unit square is there. Then the single unit squares are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, okay, sorry. This is 16. Okay, I'm sorry. I misunderstood it. So you have 17 unit squares. I'll just erase it so that you don't get confused. Okay, we have 17 unit squares. Unit squares is the single square. And then we have the 9 4 squares, and then we have the 1 16 squares. So whenever you're doing the block coding, the first thing that you have to bear in mind is that you have to try to first draw the biggest block, and then you will decrease the block size, and finally you will reach the single unit cell size. Okay. So the larger the square that can be fitted in any given region and the simpler the boundary, the more efficient block coding becomes. That is quite obvious because for this compression, our basic thing is to compile as many similar data as possible, right? So if similarity is very less and then you're doing block coding and you have a lot of single unit cells, then the purpose of this coding technique is like not that good, because our basically what we are trying to do is what? Combine everything in as much as possible. So here we were discussing the binary one. So we'll see the one which has multiple attributes over here. So if you take a look at this diagram on the left, so we have 3 different colors, Y, W and R, denoted as Y, W and R. So when you do the coding over here, so you can see the row 1 that you are seeing here. So in row 1 and column 1, we have the sizes 4, 1, 2, 3, 4. Okay, 4, and the color is R, green. In the same row 1 and the 5th position, we have one Y. Okay, I don't, okay, yeah, okay, one first row. I'll just write the number so I don't get confused. 3, 4, 5, 6, 7, 8. So what we are doing here is the first row, first column, basically we can make a 4 by 4 size of R. Okay, so 1 and size is 4, that is R. In the first row itself, the 5th one, that is like it's you have a single square, right? That's why its size is given as 1 and that color is Y. Again, first row 6, 7, 8, all those things. Why we are not considering it as 4? Because here we are not considering it in a row wise manner, rather we are trying to build the blocks. Okay, so that's the reason why it is given as 1, 1, 1, 1 like that. And then when you go to the second row, again this one is already accounted for. So then we'll go to the column 8 and there is 1. Second row, 5th, 1 and W. Okay, yeah. second row, fifth one, and W. So on and so forth. Is that clear to you? I mean, I hope I have not confused you people. Only thing you have to keep in mind is in run length coding, because I was actually initially thinking in the RLE way, but that's why I was getting confused. So only thing you have to remember, the difference is in RLE we are going in row wise manner or in one dimensional, uh, like we are going in 1D. But in block codes we are considering the blocks, so that is like 2-dimensional. Okay. Is that clear? Okay, so we'll go to the next one, that is the quad tree technique. So quad tree technique is basically more compact representation, is based on successive division of the two by two matrix or array into quadrants. Okay, so here what we are doing is, as the name suggests, quad. So basically what we are doing is we are building the quadrants. Okay, so we again have the same binary image. Okay, so the binary image, what we are doing is, this is an idealistic one. So you can see that it is a very square image, and in that we are building quadrants. So first we'll make 4 quadrants. So what we are doing is, I'm not drawing on the diagram, so I can show you here. So just imagine that you all have the, or I'll just 1, 2, 3. Just imagine these are squares. 2, 3. Okay. This is just for the sake of understanding, so it's not very neat, but then I hope that's sufficient for you to understand. So I'll just use a different color so you can. Okay. Now what we do in quad tree technique is that we will divide it into quadrants. Okay. So what we are doing is, we will divide this entire image into 4 quadrants. So if you are familiar with this graph and all those things, you know that a graph will have 4 quadrants, right? So such 4 quadrants we are building over here. So we have the numbering given as 0, 1, 2, and or this one 2 and 3 as given here. Okay, so we have 4 quadrants like this, 0, 1, 2, 3. Now what we have done over here is that, if we take a look at this diagram, okay, after dividing it into quadrants, you can see in 0 and 1 we don't have any discontinuity, like it's basically both are white completely. So there is no further requirement for dividing it into further quadrants. So we will be just leaving 0 and 1 for now. But in case of 2 and 3, we can see that there are white areas and then there are dark areas in each of the quadrants. So for this case also, again we are going to divide it into 4 quadrants. Okay, so then what we will do is, this one again we are dividing into 4 quadrants like this. Okay, so this is one quadrant. I'm sorry, my pen is not very smooth. This is another This is another, and then this is yet another one. Okay. So we are looking at the quadrant 2 right now. So it's again divided into 4 quadrants, and further each quadrant will be divided into smaller quadrants. So for example, this one you have taken. So first again this one will be again divided into 4 quadrants. Okay, so here you can see this is white, so that will be left out, and then we have these. So as many quadrants as possible we are going to build here and then give it a name. Okay. For example, that is a binary image. Now here we have an example of quadtree having multiple attributes. So here if you take a look at this, this is more colorful, so I think it's more easier for you to understand. Okay, so I think again last time's issue is coming up, so they're showing that call will end in 13 minutes. So I'll quickly make another link and I'll put it on the chat. So as soon as this link expires, please join in the other link, because last time I made the mistake that I was trying to rejoin using the same link. That's a mistake on my part. So I'll quickly make a link and share in the chat. So as soon as this one expires, you please join in the other one. Okay, just give me 2 minutes. I have sent a link in the chat, another Google Meet link. So as I said, once this one gets over, please join in that link, okay? I usually don't face this issue with Google Meet. I don't know what happened this time. I'm sorry for that. Okay, so as I was saying, so this is a quadtree with multiple attributes. So here we have another image, but here instead of just black and white, here we have a green, orange, all those colors. Okay, so if you prepare this like this, so this is the main one, and you divided it into different quadrants. So the first case, it's almost all are uniform in the first quadrant. So 1 is as such you kept it. 3 is also same, so we kept it like that. This is same, so 8 is there. But in this quadrant, you can see here that it is different in nature. So this quadrant, again we divided it into 4. So we have 7, 10, 31 and 11 like this. So the position code for this one is what? 3 and 2, because it is in the third row, second column. Okay, that is the position code value. Example 2 of this quadtree having multiple attributes. So again here you can see the first quadrant is all green, so that we can just eliminate. The second quadrant has some attributes extra. The third one doesn't, so that also we are negating. So this one and this one has some additional features. So that again we have divided it into 4 quadrants. Okay, in that the first two are okay because this is completely blue and this is completely red, so we can just leave it out. But when you come to this one, you can see there are 3 blue and 1 this one, so that we have kept it like this. And here 2 red and 2 green, so that is kept like this. And in this one we have one green, so that one green is given like this, then one set of red is there, then again red is there, but in the last quadrant we have 2 green and 2 blue. I hope it's clear like how we are dividing this. Okay, so only thing you have to keep in mind is always you will have, if you are given an image like this, first you will divide it into 4 quadrants, and whichever quadrants like one single color is present, you can just leave it. But if, for example, let's say this quadrant and this quadrant it is same, so we will forget about this. Okay, forget about in the sense that we'll just label it like this. But if there are heterogeneity in this quadrant, then again we'll divide it into 4 quadrants. Then again, for instance, like these 3 are same but this is not the same, then again 4 quadrants. So like that, basically you will reach the unit cell size. Till then you can like bring down the and divide it into different quadrants. Now here is a land use map. So in this case you can see we have guava A, B, C and D. Yeah. So in this case we'll start the root and we gave it as 0 and 1. This is 2 and 3. So this 0, 1, 2, 3, that we have just kept it like this, but in 2 there are further divisions. So we have 2, 0, this is same, then 2, again this is again divided into 4, that is 2, 1, 0, 2, 1, 1, 2, 1, 2, 2, 1, 3, this is 2, 2 and 2, 3. So we can just write it in this form. One second, my pen is getting stuck. I'll just... One minute. Okay. Okay, so as I said, in quadrant method or quadtree method, we are just making the quadrants and then we are just subdividing it to as many small quadrants as possible and then we are representing it. Okay. Another one is here. So here you have a vector image and you have a raster image. So most of the time what happens is here the edges are very smooth. So you can see its raster representation is like this. So if you remember this raster to vector conversion or vector to raster conversion, most of the time there is a possibility that the data will not be complete. Like when you look at the image, it might look very similar, but when you go into details, some of the intricate features might be lost. But anyway, this is how area is represented on a map and how it is represented in a quadtree representation. So here you can see, right, this is the first division of quadrants. Then here they left it alone because everything is almost same. But here you have the white and this thing. So again they divided it into another set of quadrants. So here these two are same, so you left it alone. Then again you divided this into quadrants. This two was fine, so then we took this. Here we have single units, okay, and this one also again we had divided. Similarly, if you take a look at this, like this also, so heterogeneity is there, so we can again further divide it. This is same, these three are same, so we'll just leave it alone. Then this will be there, these two are same, this is slightly different, so that is how the basic thing is, as the name suggests, you have to build the quadrants. Then sir had also discussed about this Huffman coding. So Huffman coding compression technique involves preliminary analysis of the frequency of occurrence of cell values. Here the frequency is considered. The technique creates for each symbol a binary data code, the length of which is inversely related to the frequency of occurrence. So here you can see, for example, this image with multiple attributes. So you have blue, red and green. So here from the image itself you can understand that the frequency of red is more. So that frequency is noted. So again, frequency versus cell values, if you see, red has more frequency followed by blue and then green. So here this pxi is the number of occurrence of a pixel with a certain intensity value, and total number is the total number of pixels in the input image. So total number of pixels in this input image is 64, okay, because this is like 1 2 3 4 5 6 7 8, so this is 8 into 8, so that is a 64 cell image. So this you can see, for example, they have given the example for blue cell. So there are 16 blue cells, you can see here 4 and 4 by 4, so it is 16. So 16 by 64 will give you 1 by 4, that is 0.25. So the pxi is the number of occurrence of a pixel with a certain intensity value, and total number is the total number of pixels in the input image. So total number of blue cells by this is total number of cell in the input image. That is how they got this frequency, this thing, pxi. Okay. Now here is a run length coding exercise that sir had also given. Like you have the solution beside it, but then can you guys please try to do it on your own? Or before that, we'll do one thing. Anyway, this call is going to end in 1 minute. So I will end this call and then I will join using the link that I have already shared in the chat. Then you can rejoin using that link, okay? So that we are not disrupted in between. Okay, I think the screen is visible. Okay, so we'll give this a try. Like we'll do the compress the following raster file with the compression techniques that we have learned till now. So we have learned the uh, run length code, block code, quad tree, and the first one was chain code. So using this, we can see, right? So here again, maybe you can even do the cell value. One is length 4 in row 1, cell value 2. So this is how you have just segregated it over here. So first row you have the first cell value, which is the green color. The length is 4. Okay. Then the second, in the first row itself, we have the orange color. So that is like cell value is 2, orange color is again 4. Same thing, 1 and 2 cell values are present in the second row also. So that's how they have done this. So 8 by 8, which is like, this is a 64, 1, 2, 3, 4, 5, 6, 7, yeah, 64 bytes image. Based on this code, we have made it into 66 bytes. This is an exercise that you can also try. You might have already tried, but then from all this idea that we have gained, this is something you can do. Then again, they have written it like this. That is like in the first set, S is like 4, and that end position we have marked. So end position is 4, and here the end position of T is 8. Okay, so I'll just number it 1, 2, 3, 4, 5, 6, 7, 8. So S, this is 4 and this is 8. Again in the second row it is 4 and 8. This is 4, 8, but the color has changed. It's U. Again 4 and 8, S and U. Here when you see, we have V in the V2, W4, X8, V2, W4, X8. Then here you have Y2, Z4, X8, Y2, then V3, W4, X7 and V8. So when you do this, we have the 44 byte diagram. Then other compression that was discussed was LZW compression, that is Lempel-Welch compression technique. This is basically, that name came from the surnames of the people who found this compression method. So this is again a lossless data compression algorithm which works by replacing sequences of characters with shorter codes, reducing file size without losing the information. It is widely used in formats like GIF and TIFF. It is also suitable for compressing the text files. So again, there are a lot of terms, but what we are basically doing is, for example, this is an example that I'm giving, how it is done in case of text file. So imagine you are reading a book and you notice that some words or phrases are repeated. Like if you read a story book, you hear that once upon a time or the princess, like some fairy tale book you're reading. Okay, so such terms are there. So instead of writing them out every time, you decide to replace them with shorter codes. So for example, once upon a time, you are giving it as hash, like in number 1, and the princess, you're giving it as number 2. So every time, instead of writing once upon a time there was a princess, once upon a time she went on an adventure. So instead of that, what we are writing, this number 1 and 2. Okay, so 1 is basically once upon a time there was the princess, so that is 2. Then once upon a time is again given as 1. So this is like we are assigning some codes so that you can just shrink the file size. That's it. Unlike earlier approaches known as LZ77 and LZ78, the LZW algorithm does include the lookup table of codes as part of the compressed file. So this is, how do you say, like it's like having a dictionary basically. Like you are assigning some kind of code for certain objects or values, whatever it is, so that you can look it up and then it's easier for you to compress it further or decompress it. The decoding program that uncompresses the file can build the table itself by using the algorithm as it processes the encoded input. That is the reason why we always earlier versions didn't have this directory, but then the latest LZW version has the directory, so they know like for what code is used for which entity. Then this JPEG compression is there. This is a very lossy compression. We are very much familiar with this file format, right? JPEG or JPEG we say. So that is Joint Photographic Experts Group, is an ISO group of experts that develops and maintains standards for a suite of compression algorithms for computer image files. So JPEG, which is usually pronounced that is as JPEG, is also a term for any graphic image file produced by using a JPEG standard. A JPG file is created by choosing from a range of compression qualities, actually from one of a suite of compression algorithms. When one creates JPG or convert an image from another format to JPG, question is asked to specify the quality of the image you want. So basically what happens is, sir has also told about this. So like for instance, we buy this very big cameras, right? Like phones with very good cameras, megapixels is very high and all those things. But the problem is that you are clicking a very high quality image. But if that image is stored in JPG format in order to save the storage space, then essentially we are losing the quality of that photo. Original quality will not be retained if the photo is being saved in JPG format. On the other hand, if it is like saved in other formats like TIFF or PNG or RAW file kind of thing, then it's at least easier to go back to the original image. But if the image has been stored in JPG format directly, we will not get the good quality image back. That's why we call it as the lossy compression, because you cannot revert back to the original one. Then sir had also discussed about MRSID or Mr. SID, that is Multi-Resolution Seamless Image Database. That is an image compressor, viewer and file format for extremely large images. This is mainly done or used in case where you're dealing with huge files like satellite images and all. Okay, so this was created by Lizard Tech and works by putting together hundreds of small image tiles into one large seamless image that can be compressed and decompressed with little or no degradation. The benefit of Mr. SID is that that it's like, you know, small, like how you build a big puzzle. So like that small pieces are kept together to generate the whole image. So that compression or decompression, whatever you are doing, will not directly affect the quality of that image. Only problem associated is the long time that it takes to open very large files. So if you are familiar with dealing with this satellite images, or like if you have ever used the USGS Earth Explorer to get, like for example, India's satellite like Landsat images and all, then you might understand, like when you try to load it, it takes a lot of time to load the image because it has a lot of information and like it's a huge one. So that is the only problem that has been there, but otherwise quality wise it retains the image quality. So how they overcame that problem? They overcame that problem by giving the user the ability to decompress just the portion of the image they wanted to view. The user can move from one part of the image to another quickly without having to wait for the entire image to decompress. So what they did is, like this option, I think it is present in USGS Earth Explorer also. So what they do is that, as I said, like let's say it's a very big image. Okay, this is a big image, and what they do is, it's basically a collection of small image tiles. Okay, this is image tiles. Now I want to see this portion very clearly. Okay, so they gave the option to just decompress only this portion and view it clearly, because earlier the problem was that when you decompress, the entire image has to load, and since it's of high quality, it takes a lot of time to load. So what they did is, they gave the option for us to select a part of that image that you want, and then only that part will decompress, so that other parts will stay compressed and this part can load instantaneously. Then another one is pyramids. So pyramids are reduced resolution representations of data set and are used to improve the performance. This pyramid method is mostly like in case of Google Earth, this can be noticed. So they can speed up or improve display performance of raster data by retrieving only the data at a specified resolution that is required for the display. So when you zoom in or zoom out, so according to your requirement, only that region will be of data will be retrieved. So as you zoom in, layers with finer resolutions are obtained. Okay. So for example, here this image is shown, an example of two levels of pyramids created by raster dataset. This is in the zoomed out stage. So here you will not see much of the details, but as you zoom in, you can see a lot of details can be seen here. I'll show you the example using Google Earth. And just give me a sec. Okay, so in case of India, let's say. So now it is in the zoomed out form. So now I'm going to zoom in. Okay, let's say we'll zoom in somewhere here. Randomly I'm zooming in. So as you can see, now all I can see is like basically not much of variations I can observe here. So I'll just zoom in further. So as much as I'm zooming in, finer details can be easily understood. This is the pyramid technique. So wherever, like at what resolution I want to see, only that resolution data is retrieved. That is what a pyramid method is doing. Okay. So I'm again zooming in. See, such details were like, for example, right now you can just see some water body or something which is present over here, but we can't actually understand what that is. Oh, now again I'm zooming in. Okay, that's I think a patch of vegetation or water body. I'm not that sure. We'll zoom in again. Okay, that's a forest cover area. Okay. See, all these details I'm getting as I zooming in. Or we'll go to some area where there are buildings. Or we'll just take this area. Okay, so here all these details are there. Okay, so all these details like paddy fields are there, buildings are there, some pathways here, all those things. But as I zoom out, the details are going to reduce. You will not be able to see that many details. So this is basically what the pyramids method is informing you or giving you. So how does it work? The highest resolution image, which is largest in size, is the base level or level 0. Okay, that is the highest resolution. The image is downsampled or scaled down step by step to create smaller versions. Each new level in the pyramid is usually half the resolution of the previous one. That is what is given here. This is like 2:1 ratio. Like that, that resolution is decreasing. Okay. This is high resolution and this is like low resolution. Instead of keeping just one large image, multiple levels are stored together. When a user zooms out, the system loads a lower resolution version for faster display. When zooming in, a higher resolution version is loaded. That's why, like, when I was zooming in, it was taking a little more time to load the features. But when we zoom out, it's like a bit more easier because that many details need not be accounted for. Okay. Then there are different resampling methods, but we'll not discuss this in detail right now. We'll just give a gist of what it is. So the three methods mainly used are nearest neighbor, bilinear, and cubic convolution. So in case of nearest neighbor, that is the default and typically works for any type of raster dataset, though it is recommended that you use nearest neighbor for discrete, like nominal data, if you remember. For that, or raster datasets with color maps such as land use data, scanned maps, and pseudo color images. Bilinear interpolation or cubic convolution should be used for continuous data like satellite imagery or aerial photography. And although this bilinear interpolation is performed more quickly, the result is not as sharp as the result of cubic convolution. It's basically like it's based on your requirement, like what do you want. So according to that, we will choose the resampling methods, but we'll discuss these resampling methods in a little more detail in the next session. I don't think we'll have that much time in today's session, so we'll discuss that in the next one. Then sir had discussed about georeferencing. So georeferencing also, it was a very big topic, so I could only include few part of it in today's slides. And next class I will discuss it in a little more detail, and also maybe I'll show you how it is done using QGIS, because I do not have the licensed software with me. So, and maybe you can also do it along with me. Okay, so in this case, transformation of data which may be in geometric domain to the geographic domains. Basically what you're doing for georeferencing is that, let's say you have a image or you have some map photograph. Okay, let's say you have an India map photograph with you. This is a like photograph only, but then you need to digitize it. Digitize it in the sense that, like how you can pinpoint a location and everything, so like that you need to make it. So first you will digitize it, so it comes into the geometric domain, that is, it is in the image format. Then you have to change it into the geographic domain, so that latitude, longitude values are inserted into this particular image, so that you can just see the locations and like use it for this location purpose. Okay. So georeferencing is the process of assigning real world location information like latitude and longitude to image or map, so that it can be used in a GIS system. Okay. So to use some raster data sets in conjunction with your other spatial data, you may need to align or georeference them to a map coordinate system. So what we are doing is that, I think I have an image also, maybe I'll show with that, that's better. So a map coordinate system is defined using a map projection, a method by which the curved surface of the earth is portrayed on a flat surface. Because we know that earth has a somewhat not completely round structure, an elliptical spheroid structure. Okay, so but when we are mapping the locations on the earth, we can't do it in this format, right? So we will use some projections and all those things, and then we bring it to the flat surface instead of the curved surface. So georeferencing basically transforms images or maps from geometric coordinate system to geographic coordinate system using a base map. This also I will show you on QGIS. But basically what you can do is, like, even the Google map can be used as a base map. So what we do is, when we work with this some image we want to georeference on QGIS, so what we will do is, we will load that image first, and then we will also load the base map. Okay, like we'll load the base map, we'll keep this on top of that, then we will do the georeferencing. So how do you do that? We establish the ground control points. So when an image is acquired from satellite, the resulting image has certain systematic and non-systematic geometric errors introduced through sensor distortion, scan skewness, panoramic distortion, and attitude of the platform, etc. So what you have to keep in mind is that our Earth is rotating and also revolving. The satellite also, with some calculations, we have placed it, but it's not necessary that it is like exactly it's able to capture all the images. There can be some sort of distortions present, like for example, one image is captured, there might be a slight gap before it is capturing the next image. So by that time Earth might have rotated slightly. So such errors can be there. So we have to account for errors at every stage so that it's not carried on to the next step. So the systematic distortions include cross-track scanner distortion, like there is a scanner which is present in the satellite, which basically sweeps the surface, like takes image of the surface by like a cross-track method. Okay, so there can be some problem with that scanning. Then mirror velocity variations can be there, like this is the nominal velocity, but then actual velocity might go like this. So that can cause distortions in the image, or there can be a skewness, like not exactly straight, but there is a slightly tilted form of the scanning that is done and the photograph that has come out. Non-systematic distortions include like earth rotation can affect it, altitude variation can affect, pitch variation. Pitch variation means, for example, the satellite or even the aerial photography, like flight, the movement of the flight can cause it. Spacecraft velocity, roll variation, yaw variation, all these things. Like you just have to remember, like there are systematic distortions, non-systematic distortions, which can result in some problems with the images that are generated. So here an example is given, like for example, this is the ideal form in which how you should get the image, like proper grid one. Okay, a unit cell is square in shape, the whole thing is in rectangular shape, but scanner image can come like this, where you have such rectangles instead of squares. Roll distortion can come, that is like up and down movement of the flight can cause roll distortion, so it can come like this. Crab distortion is like wind can affect the movement of the flight, so the scanning can be slightly tilted, which is coming like this. Or pitch distortion is basically that how do you say, that front part moves a little, front and back, tail end instead of the side, front and back will move, so that can cause the pitch distortion. So basically we need an image something like this, but most of the time there is a possibility that we get images like this. It's not very ideal. So a common method of georeferencing or geometric correction is image registration is to statistically find a polynomial of a given order that minimizes the error in a transformation from the original image coordinates to the rectified image coordinates. So as I said, you have an image that you need to georeference. You have a base map. So first thing that you have to do is establish the ground control points, okay, GCPs. So what you do is, first we'll establish that. So for that, the transformation is found by performing a least squares fit for the coefficients of the given polynomial using ground control points that are picked by the users. So ground control points are those points which are similar in case of the image that you have and in the base map. For example, like right now I showed you the Google Earth image, right? So we can see some buildings, some bridges, some crossroads you can see. So such distinct features which are present in both the images, like the that image that you have and the base map that is present. So in both the images, the common points you will mark, those are known as ground control points, and using these ground control points, a statistic, it will be like a proper transformation of a polynomial, like we'll find a polynomial which fits that, and then you do the transformation accordingly to account for the errors. So the number of ground control points that are required is determined using this, that is p plus 1 into p plus 2 by 2. So for example, if the order is 1, number of, like, this order is basically if it is a first order polynomial that you are trying to determine, then the number of GCP required is 3 using this equation. Okay, so in this equation, if you put this 1, so 1 plus 1 into 1 plus 2 by 2. Okay, so this is 2 into 3 by 2, so this is 3. But as sir has said, so similarly you can calculate all these things. Okay, but as sir said, this based on their experience and everything, mostly we will take thrice of whatever we got here. So for example, where we are calculated 3, we prefer to take 9 GCPs. Here we'll take into 3, so this is 18 into 3, that is like 30. This will be 45 into 3 will be 63. So like that, like thrice of that we will be taking. Okay, there are even more topics to be discussed under georeferencing, and I thought instead of just discussing the like theory like this, it would be better for you to remember if I show you the like on QGIS. So today I don't think we have sufficient time for that, and like not many people are also there, so I'll show you that in the next class. So we'll just discuss 1 or 2 problems and then wrap up. So JPG image format is also a type of what kind? Destructive compression tool, constructive compression tool, simple compression tool, or none of the above? You can put the answer in the chat also. No, like it is destructive compression tool. If you remember, I was saying like all other ones that we discussed, that was like lossless compression techniques. Only JPG image format was the one which had this lossy images, because the thing is, as I said, it compresses the image and basically it loses the original image quality. So it's very difficult to retrieve the original image quality once the image is stored as JPG. Otherwise, you should have a separate file which already has the original image. If you have overwritten it and just saved it as JPG, then you will not get the original image quality. How many types of resampling techniques are presently known in GIS? Oh. Now can you hear me? Oh, okay, fine. So, do you know, like, because we have not discussed it in detail, but then this topic is there. So, how many types of resampling techniques are presently known in GIS? Okay, I think there might be some problem with the connection. You can just put it in the chat, like if you have any queries. So I can also maybe write it in the chat if that is possible. I don't know what is happening. The answer is 3. Okay, so that we have actually discussed here. Where did I say that? Yeah. So we have nearest neighbor, bilinear, and cubic convolution. These are the 3 resampling techniques. Okay. Which database model is most commonly used in GIS? Okay, the answer is relational. I hope I'm not sure if my voice is clear to you. That's why I'm giving you the answer. The answer is relational. Okay, relational database model is most commonly used in GIS. Then the last question is, what is the difference between slope and aspect? This I had told in the last class also. I mean, I have not discussed it today, but this was told in the last session. Okay, the answer is slope is the gradient directly down the fall line, while aspect is the direction of the fall line relative to north. Basically, slope tells you about the inclination, or like how, for example, if we have a hill like this, so this is the slope. Okay, this is the slope, and aspect is the direction relative to north. For example, if this is north, relative to north, in which direction is the slope going? That's it. Okay, so that brings us to the end of today's session. So if you have any questions, you can maybe write it in the chat if my voice is cracking. Otherwise, also you can ask me if, like in the next session also. Are there any further questions? Or if you want me to do something in particular, like show you something, that also you can tell me. Okay, that's okay, Tanya. Like, it's fine. Like, what I'll do is, anyway, I have recorded everything and I'll be sharing the link also. So, maybe whatever portion you have missed, you can see that on, like, I'll be sharing the link on the portal so you can check. Which portion do you want me to repeat? Okay, I just discussed this question over here. So that is like, what is the difference between slope and aspect? So this is basically like, okay, I'll just. This was the question, and I was saying that I had discussed it in the last session, not particularly today. So this is basically slope is the, like for example, it's the gradient directly down the fall line, while aspect is the direction of the fall line relative to north. So that is what I was saying was, if you have some hill like this and you're discussing about this thing, so that is the slope. Okay, this is the slope relative to the fall line, and if for instance this is the north, so we are talking about aspect. Aspect is the direction of the fall line relative to north. This is not related to the topic that we discussed today, but then I just kept it. That's it. And if there are other portions that you missed out or something, like I will give the link of this record, like this slides also I will give, and the recording is also there. So I will put that and maybe you can verify that. If not, you have any other questions, then in the upcoming session also you can ask me. So I'll stop the presentation then. If you have no further queries, then we can stop the meeting. Okay. Thank you, Tanya. Okay, thank you. I'm stopping the meeting.